Welcome everybody to the Glück seminar series on glycan arrays. The last two seminars that you heard about were software tools that can help you analyze your glycan array data. And you have seen from Akul and from Yuki, there are different ways how you can approach that and different kind of displays that can be helpful for you to look at the data, heat maps, tables, bar charts, and so on. But the most important thing was with these two tools that you still have to do the interpretation of the data yourself, right? These different displays help you to, drill down and visualize things better and, see certain things. But in the end, it's still you that has to look at the structures and then come up with conclusions saying, yeah, that is what my protein or whatever you are analyzing, that is what it's binding. And today, Zachary Klamer is going to give a talk about his CarboGrove system. And there we will see that there's also a way that the computer can actually do that for us, at least partially. You will still have to go in and have the final vote on it. But that's what his tool will show. And Zachary is actually working with Brian Harp on that software and his motive finder software that I think he will also show today. So Zachary, please go ahead.
Thanks for the lovely introduction, Renee, and thank you all for coming. It's my pleasure to tell you guys a little bit about our resource, CarboGrove, which is a database of glycan binding specificities. And we'll see a little bit about how that can help guide experimental design and data interpretation. Now, my tool probably needs a little more background than some of the previous tools in these seminars so far. So we'll spend the first few minutes here talking a little bit about the big picture, as well as how the back end of the tool works. Then we'll jump into a live demo. And then we'll come back here to talk a little about applications and how you might use CarboGrove yourself. Our work leading up to CarboGrove has touched on nearly every aspect of glycan array data. We've worked closely with array developers to design new arrays or to expand on the arrays that are already there to increase the coverage of the glycans in those arrays. We developed software for the quantification and summarization of array images. It's a single finder microarray tool. I'm not talking about that here, but you can find that on our tools page. We developed software for the interactive and automated analysis of glycan array data. That's the motif finder tool, which is sort of the engine which powers the CarboGrove database, as we'll see later. And then what I'll be spending most of my time talking about today is we've compiled the analysis of over 1,000 different data sets into a database of glycan binding specificities, which we call CarboGrove. Now, when Akul gave us this nice slide to show where we're at, I wasn't really sure where to put CarboGrove. We have a database, we've got specificities, and we've got a little machine learning powering all that. So I would say that CarboGrove really fits into this whole bottom section here, helping you across the whole area. Before I get into what CarboGrove is, I need to get some background information. One thing I want to discuss is what a motif actually is. In its simplest form, a motif is just a pattern. Most commonly, people do just a simple substructure, possibly with a restriction, such as a terminal form of the substructure or an internal form. But it can be a whole lot more than that. And this is where we started our work with Motif Finder initially. We developed a concrete motif syntax capable of defining any possible combination of glycans through a very flexible syntax. We incorporated the basic substructures, and then we added the ability to introduce variable monosaccharides or linkages, the ability to use special linkages such as skips, which denote a variable extension between a core and a terminal group, for example, as well as the ability to specifically and explicitly define which carbons can tolerate a substitution. So this let us do things that you couldn't do with a simple substructure. So we could define a motif, for example, which captured both the sial alpha 3 type 2 lacnac as well as the sial Lewis X, as you see here, capturing both of these glycans. You could define a motif which included nu 5AC and nu 5GC in a 3 or 4 linkage arrangement, such as this. Or you could define a motif which was the interaction between a core feature, such as a core GalMac, and a terminal feature as shown here. So you can specifically define the presentation of a terminal epitope as we see like this. And this is as far as the original motif finder went. It was an interactive process where you define motifs and you test them, which is a really useful tool, though it wasn't practical for routine use or non-expert use. So we went further. We developed an automated analysis tool, which was able to perform this analysis for you using a motif mining algorithm. So it would extend the motif over time, powered by a machine learning algorithm, which is the regression tree algorithm, a very simple machine learning algorithm. Now, I'm not going to go into the details of all of this today. I direct you to the reference down below here for the exact algorithm we used here. But suffice to say, our motif mining algorithm would explore every part of the motif space, from interactions to extensions to even variable extensions. Like I mentioned before, we have a variable linkage. And as I mentioned, this is all powered by a regression tree algorithm. I'm not going to go into the machine learning behind that right now, but all you need to know is that the end product of a regression tree algorithm is this decision tree type model, which uniquely assigns every glycan in the array into some combination of motifs. So for example, this glycan has this motif, doesn't have that motif, and has this motif, so it falls uniquely into one of these bins, despite the fact that it could have multiple of these motifs. This unique assignment is really essential because it makes the visualization that much easier and the interpretation very intuitive, especially in cases where, like this, you have more than one bound motif on the glycan. So we further expanded this approach to allow for the analysis of multiple data sets in a combined manner. Now, this used a multivariate analysis method. It allowed us to analyze data from different glycan arrays in a combined analysis, as well as data for the same lectin on the same array, just at a dilution curve, as we see here with this data. So what you get then is you get motif binding for each of these different concentrations and how that varies. And this allowed us to get brand new insights in the data, because we found that you could actually fit a 3 or 4 parameter binding curve to the average binding of these motifs. This is really great because it allowed us to get estimates of the apparent binding properties at a motif level. So you could get the KD of that motif, the hill slope of that motif, and the asymptote of that motif. This could actually also be done for glycans as well, as we'll see later. And in the demo, we'll be able to see how this can let us get new insights into our data. So now that we had a tool for the automated analysis capable of doing things that no other tool was able to do, we wanted to improve the accessibility of this information so that researchers would be able to make use of data-driven binding specificities rather than relying on manufacturer specificities or literature-given specificities. While literature-given specificities can be good, oftentimes it ends up like a game of telephone, where from paper to paper, the specificity gets lost or changed, so that you start making poor conclusions about your data by using a poor definition of the specificity for a lectin or a glycan binding protein. So the first thing we did is we developed a way to generate reports from these results. These reports have tables with motif structures, plots, and we'll see all these in greater detail later, so I won't talk about them now. We then went and analyzed every single data set we could get our hands on, starting with the CFG, but then we dug around in literature and found all sorts of great data out there being published. And we worked with our commercial group, Seed Biotech, and got all the data they were able to share with us as well. All of this data, then we generated these reports for, and we packed it into our database we call CarboGrove. With that, I would like to go ahead and jump into our demo section here. You can follow along with me if you want at carbogrove.org, or you can use this QR code here to access the website. We don't have a mobile version of the site right now, but the desktop version is pretty accessible on mobile still, so I think you'll find that useful. So I'm going to stop sharing my slides here, and I'm going to pull up this. I'm going to share the website here now. Here we go. Share. So now you all should be able to see the website. Before I get into the website demo itself, I want to briefly mention here that we worked really hard the past couple of weeks here to introduce a new update for CarboGrove. So if you've been to CarboGrove before, you'll see new things here. We're still in the middle of that update, but the update is basically taking all of the results and updating them to use the latest version of Motif Finder. So the reports themselves are going to be a lot more interactive and easy to manipulate. And you'll actually see that these reports now are able to mine the non-glycan components of glycan arrays. So that includes things like the spacers or other non-glycan elements of the arrays. And we'll see how that lets us get new insights later. But since there's currently halfway through the update here, we'll see that the database includes both the old version and the new version. And we'll look briefly at both of those as we go through here. So when you first reach the database, or the website here, carbogrove.org again, you'll find you're greeted and some brief instructions on how to use it. The main way, though, the main thing to look at here is the search bar here. This lets us look up any lectin we want. Now, we could just hit search here, or we could type in a name. And this name search thing here actually uses different lectin aliases, so that way you can pretty consistently find the lectin you're referring to. So, for example, one lectin people might refer to as LCH, sometimes called LCA. But if I type in LCH, I'll still get LCA. Same thing if I do something like GS2, I'll still get GSL2. I could do GSL2, with the numeric form rather than the Roman numerals. Again, it gets me the lectin. So you're going to pretty consistently be able to find it if the database has it. In some cases, such as if we search up AAL, there are actually a couple lectins in the literature which are all called AAL. So they both pop up here. So most people, when they think of AAL, are referring to Alluria arienta lectin, but they might also be referring to Anguilla glutenin, sometimes called lectin. In literature, they use lectin and the glutenin mostly interchangeably. Now you can see for any given search here, we can scroll through, there's a lot of results that show up here. The three main differences between these are going to be your protein source. That's typically going to be EY Labs or Vector, but there's a couple other sources that people might use. The next column here, model complexity. And this refers to the settings used for Motif Finder analysis. Each one of the data sets actually in here was analyzed at 3 different settings to allow for a simpler model versus a more complex model, or default model. We've actually gone through and manually curated the whole database to show basically only the ones that have the best interpretability. Excuse me. The next column here is the data source column. This is the one of the most differences here, and this refers to the glycan array used in the analysis. So you have like your CFG, as well as a bunch of different literature sources and a bunch of commercial data sets as well. For any one of these, you can, of course, click on it. It'll link you out to the source. CFG brings me to the CFG website. This might bring me to the individual paper used, and so on. As I mouse over each one of these ones, you can see that it becomes highlighted. That means you can click on it, and you can see more information about the data set used. For example, the catalog number is the catalog number from the provider. Protein species is the species. In this case, it's pretty obvious. It's in the name. Protein info links us out to Unilectin 3D, which is going to give us sequence and structural information for this lectin. The PFAM section here is going to link out to the Interpro database, which is going to basically tell us about other proteins which have very similar protein folds to this lectin. This last section here is the version I was referring to. I mentioned that the old data is all run with 2.2.5 version, whereas the new data is all 3.1.1 version. As we finish wrapping up this update, we'll start to push the 2.25 to the background, but right now you see them all mixed into each other. And then down here, we have a table of the data sets used in the analysis. As I mentioned before, we're able to simultaneously analyze data sets from the same sample with different concentrations. So you see there's 5 different data sets here for this AAL data set. If I were to click on any one of these here, it would link me to the specific data set wherever possible, such as this one brings me to the specific CFG data set used for the analysis. Excuse me. All right. So I mentioned these reports a couple times. We're going to briefly look at the report for 2.2.5. That's the view button here, which links us to the report. And then we'll jump in and spend more time on the 3.1.1 version. So if I hit view, it's going to automatically open up a new tab for us. And you can see there's the tables. I mentioned box plots and more tables, more block plots. You can see these old reports. You have to do a lot of scrolling to navigate, and each one of these figures is completely static. So I want to spend more time actually looking at the new reports for AAL and P&A. So I'm going to open this one up here, and I'm going to search up one more left I want to show you guys, which is P&A. I did some research and looking through the different data sets we have. This one had some really neat insights I wanted to share with everybody. Let's see, that's the old version. It's the new version, so we'll open that one as well. So you can see as we get here that the new reports look quite a bit different. They're not super long like the old ones were. Instead, we have it broken up by tabs along the top. And rather than being static images here, you can actually mouse over all the elements in the new reports. And you can see exactly what the glycan is, each data point is referring to. And if you were to click on them, it'll actually link you out into Glygen, where you can see more information about organisms and other proteins this has been found on. So we found this to be really helpful for exploring the data in a meaningful way. We're going to go through each one of these sections in turn here. The first section I want to talk about is the array chart section. This is basically the simplest possible presentation of glycan array data you can have. The y-axis here is the observed binding, typically in RFUs, whereas the bottom is just the individual glycans, in this case clustered. Now, we don't have the time or ability to manually define which glycan families to highlight here, so we developed a system for automatically doing that. In this case, it only really pulled out OGalNet Core 1, but if I go to the AAL data set I mentioned earlier, you can see that there's the fucosylated family, lacnac family, the minosylated family, the silated family, etc. And it basically tries to pick a set of families that are most informative for the data set. So go back to P&A. Also, one thing to note while I'm here, there's these sort of sub-tabs at the bottom here. The old reports, if I go back to one of those, are only able to show a single concentration at a time. But since we're analyzing 4 or 5 or more concentrations at a time, it's helpful to be able to click through here and see how the data change the different concentrations. And we'll see how that helps us explore the data later. So that's all we're talking about for the array chart section. Oh, I should note the KD column we'll come back to later after we discuss the binding curves. The next section I want to look at here is that of the primary motifs. We found it to be very helpful to break down the reporting of glycan binding protein binding first by the primary motifs, which are sort of like the major modes of binding, and then the fine specificities, which are variations on those primary motifs, which result in higher or lower bindings, basically things that might also be found, which could adjust binding, essentially is how you look at that. And we can see for P&A, we have 2 primary motifs, as this box plot shows. If I scroll down here, we have a table which shows the IDs, the structures, the relative binding, and the number of glycans in that different group. Now, if you're familiar with lectin P&A, this first primary motif is going to be pretty typical of what you expect. The gal beta 1,3 GalNAc epitope. You can note that this doesn't have any R's on this gal, so it cannot tolerate the silated form of this. The next one, however, B, is sort of unusual. It's actually binding a terminal glucanac structure with an extended presentation and a biantennary presentation. And if we change so we're looking at the 100 microgram per milliliter, if we change the 10, we can see why that is. Because at lower concentrations, this binding almost completely drops off. So it's high binder, only at the high concentrations. So this just kind of shows the benefit really of being able to analyze all these concentrations simultaneously. You can find something that might only occur in one of the data sets, such as this particular epitope. We'll come back to something that's quite interesting. Again, you can mouse over everything here, see all the glycans and what they are. The next section here is going to look very similar, the all motifs section. It's going to include both the primary motifs and the fine specificity variations. That A family we had before now gets split up into 4 of them, A1, A2, A3, and A0, where A0 is the remainder after you separate out the other 3. And the B family didn't get any fine specificities, it's still just B0. So now we can actually go, and I'm going to select the lower concentration so you can see what I mean. I'm going to go through some of these here quick and discuss. There's, again, the IDs here. There's this common name columns. This is basically an automatically assigned common name, which tries to basically help, wherever possible, assign a common name to a motif. It's often difficult, and these can have various degrees of accuracy, as noted here. Then your relative binding, your structure, again, number of glycans. These p-values refer to the difference between glycans with the motif versus glycans without the motif, without any motif rather, which can be helpful in some cases. The one bind specificity that's a higher binder than the primary motif is A3, and this differs from the primary motif in that it has a beta here instead of an alpha for the reducing end. And this must indicate then that we're looking at either glycolipid presentation or possibly some unusual beta presentation for an O-glycan. Traditionally, this epitope would be presented as an O-glycan as an alpha link to the protein backbone, but in some cases, the array provider might have beta presentations, such as this, where you have a beta link to the backbone. But this is a glycolipid, another glycolipid, etc. If you look at, so this is the primary motif, that's the same as it was before, minus all of the bind specificities. But then if you go to A1, you can see it's starting to use some of that spacer information that I mentioned that the new tool is capable of pulling out. And if you look at this, you'll see that this is the threonine spacer, the sort of single amino acid spacer. And it's interesting to see that it actually reduces binding when connected to the traditional O-glycan presentation. If you've read Grant et al.'s work, this actually won't be terribly surprising to you because they found that using a single amino acid spacer can actually result in weaker binding because the amino acid spacer actually presents the glycan parallel to the array surface, reducing the overall accessibility of the glycan. And so we see at lower concentrations that A1 family here is the weakest binder, but then at the higher concentrations it saturates at a similar binding as the others. Again, another thing you can only really see if you look at all the concentrations together. A2 is another interesting one. This is sort of the ganglioside presentation of the epitope. And if we look up here, we can actually see it's really just the one glycan, which is bound. This is GD1B as opposed to GT1C, I think that is, which isn't really bound at all. So it seems that these sialic acids must be essentially reducing accessibility of the epitope or maybe changing the presentation of the epitope. We'll see more about that later. Again, the B column doesn't have any fine specificity, so it's unchanged from the previous plot. The next section I want to look at, we call these motif intensity maps. These basically show the same data as the previous plot, but slightly different ways. These two plots here are actually linked to each other. The top plot here is glycan binding in raw RFUs, whereas the x-axis is the rank order binding, so they're sorted. And you can see that the bottom half here is which glycans in the top plot have which motifs. So I can actually mouse over, and you can see it's highlighted in both plots. And you can see how the marginal distribution of these different motifs look in rank order here. This can be nice because if you look at different concentrations, you can see and sort of critique the model that was built to see basically how well do these cluster at different concentrations. If it's a good motif, those glycans should be grouped for similar binding at different concentrations. And we see that to be largely the case here. A1 group, nice, A3, A0. That's doing a pretty good job. The next two plots are sort of related. There's the tree map diagram and the model diagram. These both tell us basically how that regression tree was built. The model diagram here is that decision tree I mentioned before, where all the glycans kind of flow in from the top and they flow down based on which combination of motifs they have. So you see, here's our whole A family, and the A family has sort of a subfamily where there's A2 and A3. If we go back to this plot here, we can see that everything that has A2 also has A3. So you can see how they're sort of a subfamily. And then, yeah, again, the B only has that one motif to it. The tree map diagram shows similar information, but it uses sort of like a nested rectangles idea. where the color of the rectangle refers to the average binding of glycans with that motif, and the size of the rectangle has to do with how many glycans have that motif. And through this, we can kind of flip through the concentrations and we can see basically why it decided different motifs should exist as a separate group. You can see at low concentrations, this A2 here is pretty much nothing. The B family only shows up at the high concentrations. Another way basically to critically assess the model building process. Section I want to spend a little more time on here though is this binding curve section. As I mentioned before, we can fit these 3 or 4 parameter binding curves to either the motifs or the glycans. Motifs are on the left, glycans are on the right. And you can actually go through, and if you mouse over a motif, then you can see that all the glycans and their curves with that motif are shown on the right. And when you mouse over, you get all the information for that motif, what its identity is, the curve used, its KD, asymptote, and slope. And then you can begin to look at how motifs differ in terms of their binding properties. And that allows you to make brand new insights. So for example, if you have a shift in KD, that means you have a shift in binding affinity. So you go left or right on this curve. If you have a shift in slope, however, you might have, say, a radically increased slope. That might indicate a differential affinity based on the state of the lectin. So your lectin might exist primarily in a monomeric form at low concentrations, but as it gets to a higher concentration, the lectin starts to do the multimeric form. And sometimes you'll have brand new binding pockets appear that only appear in the multimeric presentation. Similarly, with a change in asymptote, you might have an asymptote that goes up, which might indicate that you have a higher capacity for lectin binding. So maybe if you had a branched presentation of the epitope, you might be able to get more lectins to bind that spot on the array. If it goes down, then something about the presentation of the epitope might reduce accessibility of the epitope. So you might have cases then where maybe when the lectin adheres to the glycan on the array, it blocks other glycans. So you can get less lectins on the array overall in terms of number. And we see some of these things actually occur here. So the A3 and the A0 motifs, they have pretty similar binding properties. A0 has slightly lower asymptote. The A1 has a similar asymptote and slope to A3 and A0, but has a shift in KD. It slides over to the right. So it's a weaker binder. If we go back to A1, we can see that's that threonine form, that threonine presentation. Interestingly, the B motif, the one that we found wasn't sort of a classic PNA motif, has quite distinct binding properties. In addition to having that higher KD, it also has a much higher asymptote. That's nearly 60,000 as opposed to these ones being around 35 to 40,000. Additionally, it has a much higher slope. It's a 1.4 rather than the 1.19 or the 1.17. So this might indicate, as I mentioned before, you've got binding that only occurs in the multimeric form. And since it's binding that branched epitope, it might be able to have many to one binding. So this is a brand new hypothesis you can form only by being able to present the data in this sort of binding curve presentation manner. Additionally, this A2 motif, the one that had those sialic acids, has a much lower asymptote. So it may be that if we go back here, that these sialic acids, for whatever reason, affect the presentation of the typical binding epitope, gal beta 3 gal mac, thereby reducing the capacity for binding. You can see as I mouse over, there's sort of two curves. The one binds, the one doesn't. That's pretty obvious when we look at it this way. You can also do the reverse and mouse over on this side. For each time I mouse over, you can see that on the left-hand side are little ticks. These indicate where the asymptote of different curves are, so you can kind of get a sense of how they cluster. On the bottom here are similar ticks. These indicate where the KD for each of the curves are. Again, you can look at kind of how they cluster in margins. Some of them, like these, actually have asymptotes which fall off, so you don't see their ticks here. Another way to view the data is using sort of scatter plots of these binding properties. So if we mouse over, each one of these has a separate KD, asymptote, and slope. And we can make plots of the asymptote over the KD or the slope over the KD. Now, in this case, the slope plot gets kind of messed up because of that one non-binder, which is part of A2. But in the top half of this plot, for sure, you can see a clear separation between the B family and the A families, where the B family has that higher asymptote and has that higher KD. You can kind of see here that slightly higher slope, but it gets kind of washed out by that point down there that the B family has. Similarly, there's a table of all this information here for each of the glycans. Right now, you can just click through it and you copy and paste it if you want. We're hoping to make that more accessible in future versions of the reports. The last column here isn't going to be of general interest, typically speaking. It has the KDs and asymptotes for each of these motifs, as well as various presentations of the structure and the motif text if you're going to put it into Motif Finder directly. We're not going to worry about that for right now, though. I mentioned before there was KDs for each of these plots. That's drawn from the KDs of the individual glycans from this plot here. So if I go to all motifs, for example, I select KD, and you can see the same exact data as the RFU values, but it's KD now on the y-axis. Recall that the lower KD is a higher affinity because that's the concentration of half maximum binding. And we can see the A3 and A0 are the highest affinity binders, whereas that B group is that really lower affinity binders with KDs around 100. Data points highlighted in red indicate that we can't accurately measure the KD because it falls too far outside our linear range. So we have, or from our data set range, rather, experimental range. We have 100 to 0.1. So we just kind of get thresholded off at 1,000 so we can't make a curve for those basically. The same data down here for the KD information as well. That's true for each of these plots, motif intensity plots. I won't spend a lot of time here. You can see each one of these also has KD level information, which is a nice, interesting way to look at the data. I'm going to go back to CarboGrove now here and show you some of the other features. So we saw the view button for each of these data sets. You can also hit the download button. If I do that right now, we'll see it downloads a .gbp file. These .gbp files are a file format recognized by Motif Finder. So Motif Finder you can download from our tools page. It's free for non-commercial uses. And you can load each one of these model files into into Motif Finder. You could define a list of glycans and make predictions of binding to those glycans for each of these models that you make. This can be nice for visualization purposes or for downstream analysis I'll show after the demo. In other cases, you might not actually know what lectin you actually want. Perhaps you're interested in an epitope, but you don't know what binds it. This is especially the case for non-experts in the field. To do that, you simply clear out this keyword column, and you can select the sort motif section here. And this has a list of predefined motifs, which you can sort all the data by. I'm going to pick one here if I can find it. Lewis X. If I hit Lewis X in here and I hit search, I will get the whole database. So you can see there's a lot of results now, but they're all sorted by their affinity and specificity for this Lewis X epitope. So the top hits make sense. You see an anti-Lewis X antibody, another antibody, anti-CD15. CD15 is another name for Lewis X, so that's another thing we expect, as well as lectins, which have a high affinity for this Lewis X epitope. AAL is a fucose binding lectin, which also makes sense. If I click view on one of these, yep, that's the Lewis X epitope. If you're interested in a more advanced filtering of the data or searching the data, you can hit this advanced button here. This is going to bring you to a different form of the same search, but you have the ability to filter down by all of the different columns from the previous. So I could, for example, select just vector. I could filter down by the protein fold family if I wanted to. I can select model complexity. So I mentioned before, model complexity refers to the settings used for Motif Finder. You'll find that it's currently set to suggested. So that's basically the ones that I filtered out as being most informative. But if you want to see all of them, you just select all here. I can select source here. I can see all the different arrays used in the analysis. I can select Z Biotech, for example, and hit search. And I can see all the data we have from Vector and Z Biotech. The next section I want to bring us to is the API section here. If you're unfamiliar with what an API is, the idea is it allows you to have programmatic access to CarboGrove. Now, some of these features are now actually currently not working as we're still in the middle of that update. But one section I want to show you especially is the list GBP So that's going to refer to listing the glycan binding proteins. And one way you can use this, just for example, I'll do it in the browser. You could obviously do this using curl or any other web getting tool. So I can drop this in here. I can set search equal to AAL, and we see that it pulls a JSON object file which contains information for AAL. So this would let people have access to that alias-based searching system that we used here, so they can uniquely collate each of the different literature names into a standardized name for the lectin. So you can do all the same things you can do with the rest of the CarboGrove. You can search for results, you can pull those results, search for data, pull that data. You can also download all the data from the database that we used for the analysis. I will note this will be updated after I finish the update as well. So maybe wait for that. Jumping back to the main page here, the last section I want to show you in this demo is the tools page. So if I go to tools, this will let us have access to the motif finder tool. So the motif finder tool itself can be downloaded from our tools page here. So I go here, PobLab tools, you can fill out this request form and get access to it. But if you aren't able to do that for whatever reason, you can just use our web server. This web server, it is a web server, so you have to upload your data to it. You can upload one or more data files. Those could be CFG data sets, or they could be any generic glycan array data set. You can download example files here, or you can see exactly what that file format is, as described here. You can upload any number of these files for the analysis. Your data itself will actually only live on the server for the time it takes to run the analysis. That analysis might take 5 to 10 minutes or longer if a lot of people are using it at that time. You can change the name of your results, and you can set various settings. There's lots of options here. I won't go through all of them here. And you go ahead and hit run, and it will upload the data, run the analysis, then it will eventually return for you a report, kind of like the ones I showed you. Now, this currently only uses version 2.2.5 of Motif Finder. That's the old version I showed you. We'll hopefully get that updated too as part of this update. So that's all I have to show you for the demo section here. I'm going to stop sharing again, and I'm going to jump back to my slide presentation. So you guys all ought to be able to see my slides again now. And I'm going to briefly talk about applications of CarboGrove, how you can use it, how we've used it, sort of inspire you to get using it yourselves. As a common question I hear from people is, I have something I'm interested in, an epitope of some sort. What lectins do I use? How can I design an experiment to ask and answer these kind of questions? One example we've had before is we had some mass spec data on PDAC samples, and we found in that mass spec analysis that there was a terminal hexac motif, which was particularly interesting, but we didn't know the exact isomer of the hexac motif. So we had to design an experiment to be able to probe that kind of question. So first thing we did is we searched CarboGrove using that motif sort feature to get a wide range of terminal hexac glycan binding proteins. We then defined a list of glycans which had that particular variations on that particular epitope. So you could have like, alpha galmax, beta galmax, alpha glumax, etc. And then we went and uploaded each of these downloaded models into Motif Finder, made predictions to binding to each of these glycans, and built up this neat little heat map for us. From there, we simply had to select a set of lectins which met the experimental needs and gave us as much information as we could possibly get here. What we ended up deciding on was the GSL2, which bound terminal glucanac structures. We selected HHA, which bound terminal alpha galmac structures, VVL, which bound terminal beta galmac structures, and PHAE, which bound the bisecting type glucanac. And from there, we were able to ask and answer that kind of specific experimental question. The other way in which you can use CarboGrove results is to actually insist on the interpretation itself. Now, the simplest form of this is if you observed a lectin was either statistically significant or just biologically relevant for your sample, you might just go to CarboGrove, look it up, and see what it binds. And that's nice. But another approach that we've been pushing very hard in our work is sort of this automated semi-quantitative analysis of um, glycan binding data. We first pushed out this idea back in 2018, and we're expanding on that currently. How this looks basically is you would take CarboGrove, you would download the models that are corresponding to your lectin binding data. You would define a list of glycans that may exist in your sample, make predictions of binding to those, and then you would solve for a linear combination of hypothetical, theoretical glycans, which basically best replicated the observed binding data that you collected. Now, this gives you an estimate basically of the relative abundance of each of these glycans, while that may or may not actually reflect the actual abundance because we have a limited set of lectins. We found that on the motif level, so you might have the right, on the motif level rather, you see surprisingly good accuracy. You might get the right amount of sialic acid and the right amount of terminal glucanate, the right amount of N-glycans versus O-glycans, for example. We've further expanded this approach in our current work, where we have taken the parent binding properties of motifs from our CarboGrove results, and we've used a sort of simplified binding model where we assume basically there's a single binding pocket to multiple ligands to actually simulate the kinetics of these binding to be able to better quantify the amount of hypothetical glycans in the sample, and thereby the amount of terminal and core motifs in the sample. And we've seen really good success with that, so I would look for publication in the next couple months as we put that together. With that, I talked quite a bit. I'd love to be able to take any questions. For those who haven't had a chance yet, please check out carbogrove.org, or if you're interested in some of our other tools, the HobLab tool page here has all that for you there. Special thanks to my PI, Dr. Brian Hobb, as well as some interns working with me on parts of this project, Anna and Lei, and our collaborator, Z Biotech, Jian Zhang, for all of their insight into the development of Motif Finder and CarboGrove. So yeah, I'd be happy to take questions.